us, and he's going to tell us about non-locality, non-isometry, and non-factorization.
Yeah, thank you very much for inviting me to present this talk, and I'll be talking about some work that I have recently worked on, and something that I have been thinking about for the last few years. And these are my collaborators, Arnab Kundu, Arnab Kundu's ex-student, Shuman, who is in Johannesburg, Johanna Ardmenger, and two graduate students. He worked with me, and now he has left physics, and he's another guy who has been working with me, Jonathan and Moritz. Okay, so let me start from the motivation why I am interested in this problem. So first thing is that whenever we first discuss black hole thermodynamics, the important thing about black hole thermodynamics that you understand black hole physics as a thermal physics with geometric identifications of thermodynamical variables. And ADS-CFT, why it is interesting is that it provides a more precise manifestation of this geometrization. In a black hole in ADS is as an explicit dual to a thermal CFT, and the holographic dual of thermalization being the formation of a horizon. And a very famous example that I will be talking a lot about is the example where a thermophile double state, which is an entangled state of some left part and the right part. These are some energy eigenstates, something, and which we sum over. And this is a thermophile double state which is dualized to a black hole, an eternal black hole, a black hole which exists for all time. So the outside is the exterior, and this is the second exterior, this is the interior, and this is the unphysical white hole region. The important reason why it entered the discussion of black hole information is that this duality, which tells you a thermophile double state and entangled state between left and right, is dualized to an eternal black hole. It is a very interesting consequence, and the consequence is the following: that think about the left and the right side without anything inside. So these are dual to a product state in a CFT. So these are like product state of two states corresponding to left and right. Now the entanglement is manifest through the fact that the modes in the left and the right, they travel across the horizon being smooth, and they meet behind the horizon. Okay, so in other words, entanglement is intertwined with the smooth horizon, which was first postulated by Van Ramstrong in 2009, because as I mentioned, the smooth horizon allows these local modes from the left and the right to go across the horizon and meet behind the horizon. And now if you complete this picture with an interior, which is the known picture for an eternal black hole, it immediately tells that the existence of a black hole interior is a geometric manifestation of CFT entanglement. So you have the entanglement in the CFT. Yes.
Sorry, I have an elementary question.
Yes.
Is the fact that it's a product state, is that an assumption?
No. This is so when you have, so this is a product state. This is not.
No, that's what when you say that it's a product state.
Yes.
How do we know that?
So we just say that, okay, so you have this is a state, this is a state, they do not talk to each other, these are completely decoupled, and if you write down the complete state, it will be a product of left and right. In that sense, I'm saying.
We just say that.
Yes.
You mean that it is an assumption?
Yes, this is an assumption that it will be a product state. So only thing is that because exactly, so it is it makes sense. It's because you have these PIs. These PIs appear whenever I have this interior. This thing. So this is a kind of a, you can say is a postulate or something, okay. And this is given by this. This is renamed as what is called this ER equal to EPR, where ER corresponds to the Einstein-Rosen bridge, which joins this left and the right across left and the right. This is the slice, and EPR is the entanglement. Means the entanglement. In other words, the entanglement is through this interaction behind the geometric interaction behind the horizon of this mode. So this is the statement of ER equal to EPR. Okay. Okay, it leads to, this is aesthetically beautiful. You understand as you as connecting to your statement, this is, if this is an assumption, it explains a lot of puzzles, but it also gives rise to some new puzzles. And one important puzzle is the fact that the boundary theory, if you look at this boundary and this boundary where this CFT lives, this boundary theory is absolutely local. There is no interaction between them. These are some kind of local theories. However, because of the ear bridge, you have this geometric ear bridge connecting these two sides. The bulk theory is non-local. This is one way to say, but there are different ways to say that, okay, this is non-local because gravity is manifestly non-local anyway. So another way of saying this is that, okay, so you have this boundary where you can write down independently the partition function of the boundary, left boundary, and partition function of the right boundary. And if I ask you to write down the total partition function, it will be a product of the left and the right partition function. There is nothing, no interaction between them. However, for the same reason, because of this non-locality, the boundary partition function, I will detail a bit. It is really non-factorized, and then it asks the questions, okay, so people have been thinking about like entanglement entropy both in the bulk and the boundary. Then it naturally asks the question, if the boundary space-time is not factorized, how do you even think about entanglement entropy? Because you cannot, like trace out half of the geometry and think about computing the entanglement entropy. So all these questions, yes, carry on.
Maybe like coming back to Sachin's question, like I think if you take the Euclidean path integral and cut it open, the state that you get is entangled, right? I mean, so
yes.
That way, if you motivate the origin of the state from a Euclidean path integral perspective,
yes.
It's not, it's an assumption obviously, but
but I'm just more talking about the Lorentzian way of writing down. Okay, I'm not very precise about the Euclidean or Lorentzian way. I will come to that
I'm just
in a
saying
bit.
that like his question about whether it is an assumption or not, if you take the state as being the state, that hard-walking state that you get,
yes,
as a result of cutting over the path integral,
yes,
then it is very natural that it is in there.
That's correct. That's correct. That's correct.
I was just coming from the point that states can be non-local. It's algebras that are local.
Yes, exactly. So I will be making the distinguish.
Quantum field theory, the ground state of even our favorite.
Right. That's correct.
Scalar field theory.
Yeah.
It may be non-local.
Yes.
But algebras that you are studying.
Yes, exactly. So, well, I will come to this distinction because whenever I am talking about factorization, here I am talking about factorization in a crude sense. I will detail a bit because if you talk about factorization, there can be factorization of the Hilbert space. You can also think about factorization of the algebra. In general, these are two different concepts. So, one relies on whether you find a commutant or not, etc., etc. But I will come to that. Okay. Okay, so the behind the path, so there is also another interesting mismatch. The mismatch is between the dimension of the bulk and the boundary Hilbert spaces. So because of the interior, the bulk Hilbert space has a very, very large degrees of freedom. And however, we know from this, from our knowledge, that if you have a black hole space-time, the entropy is bounded by e to the power s. So we expect a large but finite amount of entropy from the boundary theory. So you have these are the two puzzles which are both are manifestations or some way of saying the information puzzle. So what we understand in the sense of it gives some aesthetic solution that quantum entanglement is a very important quantum player in this game, which we of course understand at the level of aesthetic conjectures like ER equal to EPR, but it remains technically unaccounted often whenever we are talking about really mathematical statements regarding this. And what I believe is that the resolution of the information paradox it depends whether it can be resolved or not, depends how quantum entanglement is very quantitatively incorporated in the statement of duality. So whenever we say ER equal to EPR, it gives you, okay, so you have this classical geometry corresponds to some entanglement, but if I want to understand it more technically, how really I want to include it in the duality, this would be very interesting, and we wanted to put forward some baby steps in this direction. So we will be discussing two possibilities. We will be talking about two kinds of microstates. By microstates, here I mean some states I will be considering which for a low energy observer will look like a thermal state. So this is what a very specific way of saying what I mean by these microstates. I will not talk about very general microstates and so on. And one kind of states which will have horizon, although this horizon is smooth, it's a pure state. And we will demonstrate how incorporating real Lorentzian non-locality one can resolve both the non-isometry and non-factorization puzzles. And the second class, which also Chetan works on, some microstates without any horizon, and we will demonstrate through simple toy models how an approximate thermality can be obtained from a horizonless configuration. So these are the two classes of things I will be talking about. These two scenarios are complementary to each other. Let me give a very physical intuition about this. In the first scenario, we will show that how a theory of gravity starts looking a quantum mechanical theory when the non-local corrections are incorporated. And the second one is a complementary way, and it shows how a quantum mechanical theory starts looking like a theory of gravity in a particular limit. These are the two ways of approaching the problem. First, we start from a gravitational theory and try to put some non-local corrections which are very typical of gravitational theories, and show if I properly take into account those non-local corrections, the theory of gravity looks like a theory of quantum mechanics. In the other case, we will yes, carry on.
Microstates in the horizon, what you actually mean is microstates for the two-sided.
Yes,
right?
exactly.
For a single-sided system,
Yes, yes.
really want
Exactly. I will explain these configurations in a bit, but generically speaking, in the second case, where the cases that we both consider, you do not have even some horizon nearby. So we are just saying like, okay, very completely smooth microstate. These are also smooth microstates, but these are two-sided black holes. So that I'll be talking about. That's what I mean.
So I mean, if I'm jumping ahead a little bit, but so if I'm understanding where you're roughly going to go, I would say that you're incorporating the non-local corrections to get rid of the non-locality inherent in the original two-sided.
In some sense, yes. It will be. There is a cancellation. Yeah, we will show this. Yeah. That's what I mean by incorporating non-locality, because we say like this small corrections coming from non-locality and so on. So. Because if you think about a pure quantum mechanics, there is not those corrections, and these corrections are really due to this non-locality. That's what I mean. Okay, let us talk about the first class of microstates. And the first class of microstate, as Chetan kind of correctly guessed, in fact we also discussed briefly. So these are the states which are interested in are kind of phase shifted thermophile double state. So it's a thermophile double state, but you have a phase, but this phase depends on n. So in particular, this phase, as I will explain here, okay, let us wait for a few lines. So this is the alpha state, which we call either generalized thermophile double state or phase shifted TFD state. These are only phases. So if you compute, for example, observables, this doesn't really matter. So I will explain. So this alpha equal to 0 is actually dual to an eternal black hole, and in the dual sense that I discussed, in the sense of ER equal to EPR, it will correspond to a wormhole which is opening up at T equal to 0 and TR equal to 0. Okay, this is a slice like this which opens at TL equal to 0 at left boundary and TR equal to 0 at the right boundary. Okay, so holographically these phases appear. The phases, this I alpha n that appears corresponds to the freedom of gluing the left and the right boundaries to the bulk black hole geometry. So whatever the bulk black hole, if you recall the Kruskal diagram or Penrose diagram, this is the Penrose diagram of ADS black hole. You can think of whatever inside is the bulk, and then we do this conformal compactification to put the boundaries, include the boundaries in the space time, and these boundaries you have freedom to glue whatever way you want to glue it, right? I mean, you can try to glue the T equal to 0, TL equal to 0 with TR equal to 0, or you can also glue TL equal to 0 to any other TR. Okay, so it will correspond to evolving this TFD alpha state with either e to the power one-sided evolution of TFD alpha, or you can also equivalently think of two-sided evolution. The reason you can think of two-sided evolution, because if I multiply this quantity by e to the power I T by 2 HL minus HR, it gives you e to the power I HL T. Okay, so but e to the power I HL minus H are acting on T, acting on the TFD state, doesn't change the TFD state. So either you can think of as a one-sided evolution, or you can think of as a global quote unquote time evolution in the bulk. There is no definition of time in the bulk as such, because there is no origin of time. But these things you can think of some sort of bulk Hamiltonian and evolving the slice with the bulk Hamiltonian. And if you do that, then you can identify this I alpha n with E n times t. Okay, so this is the definition of this sort of states. So now what I am saying, these are microstates. I am calling these microstates precisely because you cannot differentiate these states by any single-sided observer or by any local observer in the theory. Okay, so to detect this phase, one needs to make non-local measurement, and the physical picture is something like this. If I kind of zoom in this slice, okay, and think about this as a real wormhole geometry, you can think of this asymptotic region where you have two observers L and R who kind of synchronize their clock and jump into the wormhole from two directions, okay, from two mouths. And if they jump inside from two mouths and meet somewhere near the horizon, they will find there is a mismatch in their clock, and because of this lack of time reversal symmetry in the bulk, because there is no origin of time or no global time like killing vector and no manifest time reversal symmetry, and that will give rise to these geometric phases e to the power I alpha n.
So those
Yes, carry on.
you can think of as basically two people jumping in from.
Yes, yes. If you jump from one side, you cannot detect these phases. Okay, so that is the reason these phases. Now, there is a very one technical way to understand these phases, as was first postulated by Verlinde in a very nice paper in 2021, and this name of the paper was also very interesting. It was called Wormholes in Quantum Mechanics. The idea was that how can you see the wormhole-like structure in quantum mechanical systems, and the argument was as follows. So, if you write down the partition function, and then the partition function, if you see the partition function as two sides, one is omega, another is h dt, then, and if omega is a non-exact symplectic form which cannot be written down as d times d of sigma, if you cannot write this down, then this part you cannot separate into different boundary contributions, and if you cannot separate into different contributions, then the partition function will no longer have a factorized structure, and that is what I mean, that this full partition function you cannot be decomposed into the partition functions of different boundary contributions. Okay, so in fact, if you look at this, and in one of the papers I showed in some last year or last to last year, is that okay, so we derived this for JT gravity. If you take this situation for a simple two-dimensional theory of JT gravity, you will see that this the symplectic structure of this phase space is omega is given in terms of d delta, and this precisely gives you a non-exact symplectic structure, and can be identified with the wormhole contribution. But I will not go into this, but this is one way to see how the wormholes appear and how this alpha-ins has to do with wormholes. So this alpha-ins, yes, carry on.
Is in gravity automatically this condition of non-exactness specific?
Yes, exactly, that's true, that's correct.
Why is there just a single UN phase for each n? Why couldn't we have just done a more bigger unitary transformation on the entire right Hilbert space?
So you mean here?
Yeah, so there is just a U1 phase for each n.
Yes. So
the right Hilbert space is
you can have other symmetries, and corresponding to that you can have other. So for example, whenever you have this, you generate an asymptotic symmetry charge, right? Like this Hn you can interpret as a symmetry charge.
I'm saying just from the starting point, your first line. In the first line, why did you introduce a phase?
No, I'm just okay. So I'm just saying, like, these are the class of states I'll be talking about, and one example of how this class of states can be generated is through these sort of things. But there can be more general scenarios. You can have other.
Okay, what I mean is that there is no canonical basis.
No.
In the Hilbert's, there is no canonical basis in either the left or the right Hilbert.
Yes.
You choose a basis in the left Hilbert space. The right Hilbert space, you can choose a basis only up to an overall unitary transformation.
Yeah.
Right. So instead of alpha, instead of u1 phase times En, Would we not have had a more general unitary operator, which mixes, which makes a more general mixing in the, I mean, it's a more general.
I think,
yes.
I think you will have to pick some unitary which is part of the asymptotic
Asymptotic symmetric group, yeah.
So, but I think
this is the time translation, corresponds
yeah,
to time
just
translation.
picking one. I think there might be, so because I think it is like I've heard Strominger make statements to the effect that we don't know what the full symmetry pair of
Yes.
reality, etc. are. So I think there might be more things. I think what
So for example, whenever you are writing down the asymptotic symmetry group, you get these symmetry charges you get from some quantity like Cij. So Cij can be constant or 0. So if it's 0, you get this charge. This is corresponds to the translational time translational symmetry. But you can have other symmetries as well. You are free to choose. But I'm just giving an interpretation of these things, particularly in this talk. But
yeah,
in general, you can.
It's a time universal symmetry. I think so. That's one reason why it is.
Yes. So in this case, it is important is since we are talking about non-locality in the bulk, the non-locality becomes manifest through the lack of time reversal symmetry in the bulk. So that's what I am.
For that, you just need the J operator, right?
Yeah. But that's what we are doing, but choosing a particular one.
Maybe I will ask.
Yeah. But yes, but as Chetan said, like we have to choose one of this asymptotic symmetry group. So this is one which makes non-locality manifest.
Explain to me later.
Yeah, of course.
This is a symmetry.
Yeah, of course. We also wrote this in one of our paper. Yeah. That we'll discuss. Yeah. Okay. So it would be very clear if you just write down the boundary action. If you write down the boundary action, then you have gamma mu nu times delta t mu nu, and then you have to choose the correct boundary term, and that will fix your asymptotic symmetry. So this delta gamma will be 0. That is the standard Dirichlet condition.
As in coming from ADS-CFT?
Yes.
Boundary action as
Since we are talking about ADS-CFT, so in the gravity. So if you write down the higher dimensional action and vary this action, then for the correct variational principle to put the Dirichlet condition on the boundary, you have to set delta gamma ij equal to 0. Now if you want to fix delta gamma ij is equal to 0, you have to set gamma ij is equal to some constant Cij, and depending on different choices of Cij, we will get defined asymptotic symmetries. We can discuss this later. Okay, so very good. So these alphines remind that this holographic TFD state should not be regarded as a split state. That is a purification of thermal state, and these states, yes, is very difficult because you do not know exactly write the bulk Hamiltonian in higher dimension. For the JT gravity, you can show because in the JT gravity, if you write down the bulk Hamiltonian, it is given by the horizon value of the dilaton. So then you can explicitly write down and do the integral. For higher dimensions, you expect that same thing will happen, but it's difficult to do this computation integral explicitly. So in fact, in the JT gravity case, you can compute what is known as this Berry connection by this computing this Murar-Cartan form or something explicitly. Higher dimension is a bit difficult. Okay, so these alphines remind that this holographic TFD states, as I said, like cannot be a split state. You should not think it of as a purification of this thermal state because there is some non-exactness in the partition function, and there are infinite number of them, so they form a continuous family of black hole microstates for eternal black holes. And if you think in terms of the wormhole geometries, the dual wormhole geometries, you can associate it with the Einstein-Rosen wormholes with all possible lengths, and they are infinite in number and signifies a huge number of interior degrees of freedom. If you just remember this paper by Maldacena and Hartmann, so you kind of move this slice upwards and you kind of take all these degrees of freedom into account. So now if you think about a large enough time, so if you have a late time behavior, then this TFD alpha, TFD gamma states are approximately orthogonal, and this follows from definition because these ENs are random, and if you take sufficiently large T, then you get this TFD alpha basis becomes approximately orthogonal, and this approximate orthogonality implies that an infinite dimensional Hilbert space you can think of as low energy. However, there are connected parts of the higher moments and which are non-trivial. For example, if you consider the second moment, it will be given the first term is the product of, so you rescale with the square of the partition function. So the first term is the product of the partition functions, just like this, and the second term is a connected contribution. So you should think, okay, if I have not, yes, carry on.
That order e to the minus SPH, is it really SPH, or are you counting some states characterized by alpha, and SPH is defined as the entropy of?
Exactly. To be precise, that you should do. Later on, we will identify these two as black hole. I think yeah, it's a very good point. I should be careful actually. Yeah.
So right now it is the spacing of, the size of the micro.
Yes. So because this is given by the Z2 beta by Z square beta. So you can, that is the entropy you read off from the canonical entropy.
Yeah, so that is basically a state counting entropy of those alphas.
Yes, exactly.
Not directly there.
Absolutely. And we will identify this in a later step whenever we do this microstate counting. Yeah, very good point. Yeah. So this thing you should understand in the following way. So if you think of, so this contribution is geometrically realized as follows. You think this of, you have this TFD state, think this of as a thermal cycle, and each thermal cycle is characterized by this index alpha. Now I am talking about Euclidean path integral language, so this alpha is only an index. So the alpha previously has interpretation in terms of the phases, which are the real non-local phases that appears, but whenever you are going to Euclidean picture, the alpha only is an index which characterizes the thermal cycle. Okay, so you have this thermal cycle. So sorry, this is the contribution where you have two thermal cycles, and there are two ways to fill this up. So this you can think this circle you can think of the boundary condition, and now you have to fill it with the bulk configurations consistent with this boundary condition. So there are two ways the bulk configurations you can think of. The first way is that you fill in the bulk by Euclidean black hole. These are two independent Euclidean black holes that you can think of. These are the Sigurd. The Euclidean black hole, and then another way you can do it, you have a connected diagram where you actually sum over this gamma index. Okay, this summing over the gamma index is actually in the Lorentzian sense interpreted as a summing over the states. Okay, explicitly. So these wormholes or wormhole-like geometry that appears due to summing over the states rather than ensemble. So you have different sorts of microstates, and to get to this result, you actually sum over this intermediate state index.
So, when you, what higher moments means, you just what are you? I didn't understand what you mean by higher moments.
So I am just saying, like TFD alpha, TFD gamma in the leading order is alpha gamma. So now you can also compute the, like if you think about the random matrix language, it is you compute the variance.
What is this curly n?
Curly n is just normalization. You can think of it as 1 by z1 square, for example.
1 by z1 square.
Yeah, that's what you get this thing, and then you rescale with 1 by z1 square. You can also there are different ways to normalize. Some people also take the total number of states and normalize with that. That is also possible.
So you basically need two sides, and
yes.
So typically in these replica wormhole calculations, what happens is that you don't have states.
Yes.
What happens is that you get
very good. Yeah.
Average over replicas.
Right.
But here on the other hand, you have two sides, so that it effectively becomes a state average.
Yes, that's the point. The point is that if you think about this Euclidean black hole, so you think about this this thing, right? And you and then you put the boundary condition right here. Okay, and then in the first diagram you put the boundary condition right here and fill up with the Euclidean black hole. So you have this alpha and gamma here, and this gives you the first term is something like this. So you have these things.
I think that's fine. I'm just concerned. So in the Euclidean sort of calculation, the left-hand side object would naturally give you some particular contraction of density matrices, which is responsible for something like entire entropy.
Yeah, I will come to that.
What is the left-hand side? What does it mean?
This thing?
The left-hand side that you have defined on the...
This one or this one? This one, same thing. Yeah. So this will correspond to the, okay, so I will come to that in more detail. So if you think about the microstates, so these you can think of the first term as the leading contribution of the Gram matrix. Okay. So these are the overlap of the microstate. Yeah. Now this is the moment of overlap. Yeah. This is the moments of the overlap. So if you expand the Gram matrix, these are the subleading contributions that comes from the connected contributions of the overlap. I will give, it will be more clear whenever I write down the gram matrix. Here I just give the, the analogy, I drew this before with that.
The overlap matrix, that's what you're computing.
Overlap matrix I am computing, and that's what I call higher moments. I have in mind the higher moments of the gram matrix, but I'll be more precise what I mean. And I wanted to geometrize this in this way. So then we'll see how we use this. So only thing that I wanted to say that, okay, so this scales with e to the power minus s as also in this case. So in the leading order, we have infinite dimensional Hilbert space because they are approximately orthogonal, and the expectation is that we should get a finite dimensional Hilbert space once we take into account non-local corrections. That's the expectation. This has been an active field of research for the last few years, and the usual way to achieve this has been to introduce back-reacting heavy operators like the end of the world branes and something like that. And the general idea is to generate replica wormholes in the gravitational path integral, which are non-perturbative in entropy, which effectively reduce the dimension of the Hilbert space and gives you the correct dimension of the Hilbert space with the correct page curve, etc. So there are two advantages with our microstates, and that is the motivation that I consider these states. First of all, we do not need to add anything extra externally. We do not need any additional degrees of freedom. We use the real inherent non-locality of gravity, because these alpha phases are inherent in gravity, which gives rise to replica wormholes when interpreted from the perspective of Euclidean gravity. So 1 and 2 make the connection to information paradox, or rather the expected resolution thereof, much more transparent, because the fact here we are using is that gravity is not manifestly time reversals.
So when you say anything extra, you mean like end of the world brane?
End of the world brane or heavy operators or anything like that. So I do not need to put anything. Rather, non-locality is much more inherent to rather than anything. Okay, so now connecting this also connects to your question that, okay, so when we have these subsequent corrections you can always think of as some sort of, random matrix kind of distribution with the correct, this higher moments will be corresponding to the variance of this object, okay. However, in this case, we have to do a state averaging rather than conventional ensemble averaging, as Chetan already mentioned. And nevertheless, to derive the correct dimension, we still use the particular method of these papers by Pennington and others. Okay, so let me sketch what are the standard ways, what are the way that you achieve this correct dimension. PSSY first showed this way, then Balasubramaniam et al. They also discussed the microstates corresponding to a different end of the world branes with different, the tensions and so on. But this is roughly the scheme, how you compute it. Let us consider a microcanonical window in which the TFD states are supported. Okay, this is done by computing the TFD states, but giving a support function f, which normalizes this state and also ensures that these are supported in this window. Now we consider a Hilbert space for a sufficiently large omega, and you introduce a gram matrix, which is a overlap matrix. Yes, carry on. Omega is a very large number. So I will come to the what is a
list of alpha.
Exactly. List of alphas, so it's countably large. It's a very large number, and then you introduce the gram matrix, which are positive semi-definite by definition. These are the state overlaps, and to find the dimension of the Hilbert space, one needs to compute the actual dimension of Hilbert. If there is a repetition somehow, we have to compute the rank of the gram matrix. Okay, so that's all you have to do. And there are several ways to compute the rank of the gram matrix. The easiest way or the most straightforward way is to the Gram-Schmidt way, that you locate all the null vectors. Okay, or you can also diagonalize the matrix. However, most of them, almost all of them except the one I am going to talk about, rely on the precise knowledge of the elements of the gram matrix. You need to know exactly all the elements of the gram matrix, otherwise you cannot perform the Gram-Schmidt. So you need to know all the states and all the overlaps. So the thing that is efficient that PSSY use is the resolvent method. So you think about lambda being the eigenvalue of the gram matrix. The resolvent is defined by this object, and you can expand this and you get this leading term as delta ij over lambda, and then the subleading terms, which are that's the moments what Chetan you were talking about. You have these different moments of the gram matrix that appear in the expansion, and you can also write down the trace of the gram matrix. So as I mentioned, the resolvent encodes all higher moments of the matrix. However, it assumes a diagrammatic expansion, so you can just write it down. But once you write it down, I can write it down this way. So this is how you write down the resolvent. This is the diagram that I have drawn, but now I more formalize it in terms of the gram matrix. So the leading term is a boundary condition filled up by one of the Euclidean black holes, and these are the two Euclidean black holes, which is Z1 squared, and these are the connected contribution, which is Z2. Now you can using this Schwinger-Dyson kind of series expansion, you can just resum this series. Okay, and once you resum, you get a very simple equation of motion, quadratic equation, which you can actually solve. It's just a quadratic equation for all R you get, because this object becomes a geometric series, which you can eventually resum. And once you write this down, then you can compute what is the eigenvalue density from the this discontinuity across on the real line. Yes. So then you cannot sum it, but now whenever you can use in the Schwinger-Dyson, then it becomes a geometric series. So once it becomes a geometric series, you can resum this. That's the idea. So then it becomes a simple equation. No. I have started with omega dimensional Hilbert space, which can be arbitrarily large, but not uncountably infinity. And then I will find a constraint on the omega. So that's the idea. So I start with a very large number of omega and try to find what is the value of omega.
I just mean that sum you are taking to infinity. Like if it's a large but some finite large one.
Yeah.
After some power, it will repeat, right? I mean, because the relations. The relations is
Yeah.
But is that a problem?
No, then it will rearrange.
Yeah, I mean, but
square will have more terms and so on.
Yeah, that I agree. But
That power, n plus 1 power will be related to the lower ones.
Sure.
yeah.
That's all okay.
But whenever you are rewriting in terms of this resolvent here in the second line, it really doesn't matter. Then you can just write down a geometric series on the resolvent.
But if it is finite, then the Hamilton cascade will come down all the way till G2, G1, G1 squared.
It won't rearrange nicely in this geometry. Because you're assuming.
Okay, I can show you the computation maybe a bit later on, but yeah. So it's
Can you show the previous slide? So basically, the resolvent is you're expressing it as sum.
yes.
And then yeah, sure.
And these are basically these diagrams. But remember, this will be down by e to the power minus s. So this will be down by e to the power n minus 1, n minus 2 times s, and so on. So this will be a converging series. So if you have this contribution of two mouth wormhole, it will be e to the power minus s, 3 mouth wormhole, it will be e to the power minus 2s, and so on. So that is helpful while you resummon the whole thing, because there is a scale set by e to the power minus s. Okay, maybe you can go through the details in a bit, and yeah, the eigenvalue density, once you write down the eigenvalue density, and from that you can compute the rank of the gram matrix, and the final result is the rank of the gram matrix is given by this minimum of omega and e to the power beta h. So if you start with omega, which is larger than e to the power beta h, the rank will be given by e to the power beta h, and if you start with omega less than e to the power beta h, you will end up with omega.
What was SBH here again?
So I think, okay, I should be changing the notation. By SBH, I mean the canonical entropy.
So basically, again, it is basically defined using the states.
Yes. Okay, so thus taking into account non-local corrections, into account, the mapping into between, there are some non-trivial steps in between. For example, okay, so for example, you have this. Okay, so whenever you have this z square by z2, right? Sorry, z2 by z square. This ratio you computed using canonical ensemble. We write down the TFD state in the formal way and write down the canonical ensemble. So now in that, but whenever I define this state, this is the microcanonical ensemble. these states. Now there is an intermediate step that PSSY used and also used by Witt and others. So they kind of identify the canonical and microcanonical things by the following. So they write down this partition function and do a Legendre transformation of they make a Laplace transform of the partition function to write down the density of states, density of eigenvalues. Okay, and then multiply by delta E to give you the microcanonical partition function, and then replace in the sum. So whenever you are writing down the second term, here there is a Z2 square, Z2 over Z1 square, and that you replace by corresponding microcanonical quantity. And once you replace by the corresponding microcanonical quantity, this e to the power minus beta e to the power n cancels with e to the power minus n beta e, and that gives you the finite result. I can show you the details if
that smells a lot like how we get rid of disconnected diagrams. We do Z2 by Z squared.
Yeah.
Right?
Yes, exactly. So when we do Z2 by Z1, so is Z2 by Z1 square. Yes, exactly. So you go to the microcanonical window, and then when you kind of rewrite it in terms of the microcanonical partition function given in terms of density of states multiplied by delta E, then from this e to the power minus beta e to the power n cancels to e to the power minus n beta e, and then you get this a geometric series back. So that's the way it works.
No, I meant specifically like how we get rid of this.
Yes.
Diagrams when we do perturbation theory.
Yeah.
Favorite interaction.
Yes.
Presumably you have more terms like that.
You have yes, you have.
C1 cubed and
Yes, you have more terms, because here I have shown up to the two mouth wormholes. So you see these are the boundary conditions, these are the free propagator, then I have one boundary condition, then I have two, then I have three, and so on. So for all of them you have, for example, if you have three, there are several combinations when you have one free propagator and one wormhole, right? And then you have also three mouth wormhole and so on. So this will be the series. Okay, so thus upon taking the non-local corrections into account, at least in this particular case, the mapping between the bulk and the boundary Hilbert space does become isometric, as one would expect, and the holographic interpretation is that we are able to find that only this number of ER wormholes are sufficient to probe the black hole interior. So these are the conclusion. And then I will say a few words about the algebra of operators associated. So the non-vanishing geometric phases, they have a beautiful interpretation in terms of the von Neumann algebra. So to start with, if we forget about everything, this is von Neumann algebra is algebra of all bounded operators with certain properties. For example, this is a star algebra, forget about this. These are they have a particular property. For example, it's a double commutant, etc., etc. The algebra is double commutant itself. It acts on the Hilbert space, and one can define what is known as a trace functional, which is defined in this way. For all practical purpose, this is given by the expectation value of the commutator of the operators in this basis, and if this sort of a state exists, then it defines as tracial state, and existence of the tracial state is used for categorization of the von Neumann algebra. So there are three types of von Neumann algebra. Type 1 is for finite dimensional as well as certain countably infinite dimensional system, and typically encountered in quantum mechanics. It always contains tracial states. By what I mean by always contain tracial states, you can always define trace in the usual sense of taking trace, and that is the reason why in quantum mechanics I can always define density matrices. Okay, we always have an irreducible representation of the Hilbert space, and which is connected to the fact that you have a pure state. You can always define pure states. In type 2, it works only for infinite dimensional systems. They have tracial states. You can define density matrix. However, you cannot define any pure state. And the 3 is the most notorious. These are only true for infinite dimensional system, and no tracial state, no density matrix, no pure state. So And then what some facts from holography, what Witten told us through several papers is that this gravity at large n at classically low energy, and these are given by type 3 algebra where you cannot define a density matrix. Accordingly, there is no way to formally define an entanglement entropy, and that was the problem that I mentioned related to the non-factorized structure of the Hilbert space. And with 1 by n corrections, which are perturbative quantum corrections, the theory becomes of type 2, where you can define density matrices. I will say how, but not in a conventional way, but there is no pure state. And finally, and you can define density matrices, and then finally the full quantum gravity, and nobody has showed this, but you expect it to be type 1. This should behave, so it means if you add all perturbative and non-perturbative corrections, it will behave like a quantum mechanical theory. And this is consistent with the information loss puzzle. At least this expectation is from the perspective of information loss puzzle. So you expect a type 1, the gravity to behave like, the algebra of operators in gravity should behave like a type 1 von Neumann algebra. So now let us briefly mention about what I mean. How does this fit in this context? The algebra of operators in the semi-classical limit is of type 3-1. Forget about 1. This is type 3. This categorizes, the subcategories of this von Neumann algebra are based on on the spectrum of the modular Hamiltonian. Okay, so how they converge or something. So they correspond to continuous energy spectrum, and this is a necessary and sufficient condition as shown by Lashkari and collaborators, that these two things are tied with each other. And this continuous energy spectrum is connected to the type 3 algebra. That is what Lashkari they showed with full glory. Like they showed, like if you show, and that is also true in the case of the microstates as we considered.
I think, but it was there, it is implicitly used by Lorentzian, right?
Implicitly, but they have not explicitly proved it.
But I think they had some kind of a semi-theorem type of thing from Alain Kohns or something like that. I think
Maybe
not a full proof.
Maybe, but as far as I know, Lashkari gave this full proof about this thing, more robust proof that if you find this energy becomes continuous in a particular regime, you can associate a corresponding algebra to be type 3-1. So it's tied with the fact that the states are orthogonal to each other. Also, these states cannot be regarded as a split state. This is the reason why you cannot think it of this TFD state as a purification of a thermal state. So accordingly, these TFT states, that is what Witten taught us, do not belong to the factorized Hilbert space, and because there is no notion of density matrix and no notion of entanglement entropy. And this is the factorization puzzle that we talked about. And then Witten gave this proposal that think about this TFD state, instead of belonging to the factorized Hilbert space, think of as the ground state of the GNS Hilbert space. So you think it of as the ground state of the GNS Hilbert space and build up the GNS Hilbert space by acting with local operators on these TFD states.
Can you just remind me,
yes,
at least intuitively, what was the split state?
The split state is, for example, if you write down the density matrix and write down the density matrix, if you compute an observables A in a particular full density matrix rho, that will be given by that observable computed in left density matrix times the right density matrix. So in other words, you think about the left as a purification of right, as far as a particular local observable is concerned. Okay. So yes.
What this is basically saying that there is an alpha ambiguity in doing that.
Exactly. So whenever the idea is that whenever you set this, think about the standard ER equal to EPR, where you choose the slice to be t equal to 0, then this effect is not viewable, because you are kind of considering a particular, very particular state. Exactly. Exactly. But the important point is that Witten talks about in a general TFD state. He says like, okay, if TFD state you cannot think about as a split state, you cannot think about belonging to type 1 factorized Hilbert space, but this TFD belongs to is a bound state of the GNS Hilbert space. That Witten says. But what this TFD alpha states makes it manifest, as we showed in a series of paper last year, I guess. So is that this existence of this alpha and this non-exact symplectic structure makes it very manifest that why you cannot write this down as a vector in the factorized Hilbert space. Because if you have this alpha, as we showed, you cannot factorize it into the two boundary partition functions. So there is no way you can write this as a purification of other. So that we choose TFD as a very particular t equal to 0 slice is an accident that kind of loses some non-local details of the theory. Okay, so the GNS construction you can do for individual TFD states, as I said, like you think about the TFD state and build upon the Hilbert space by acting with local operator on the TFD state. Now, each of the Hilbert spaces that we construct where TFD alpha is a ground state can be characterized by a fixed value of alpha. However, if you are a low energy observer, you are completely insensitive to it because you do not know what is alpha. You just happen to be in a particular Hilbert space with a particular choice of identification of boundary. Now we can include the Hamiltonian to the algebra. Apart from the local operators, I can also include the Hamiltonian of the algebra. And if you include the Hamiltonian of the algebra, you end up into a type 2 infinity algebra which acts on an extended Hilbert space, and that is the Witten's cross product, where you have the GNS Hilbert space crossed with these square integrable functions L square. So it includes all the TFD states. So the pictorially, this is as something like this. So you have a TFD alpha state, which is a ground state of a particular GNS Hilbert space, and then you build up the Hilbert space on top of that using local operators in this Hilbert space. Then you have another Hilbert space with a different index, and then another Hilbert space here. But we know from one TFD to alpha to another TFD alpha, we can go using the Hamiltonian. That was the very first slide. If you just evolve with a one-sided Hamiltonian and you go between these two TFD states, therefore if you include the Hamiltonian in the algebra, you can just go from one GNS Hilbert space characterized by a particular value of alpha to another GNS Hilbert space with another value of alpha. Okay, so that gives you a larger Hilbert space, also infinite dimensional, and you can show this is actually type 2 infinity, where you can define the cross product. Since it is a cross product Hilbert space, you can definitely define trace, but this is not a decomposition into left and right. Okay, this is a different decomposition. Now the last part of it is that including all the non-local corrections of the Hilbert space, algebra of Hilbert space becomes finite dimensional and the spectrum becomes discrete, and the associated algebra of operators becomes of type 1D with D is equal to e to the power s black hole. Again, I mean the canonical entropy, which you can identify with the black hole entropy later on. Now this TFD alpha states after you.
But that is one of the crucial points.
Yes.
That particular thing,
yes, exactly.
If you could show that it was the area of the black hole somehow implicitly, then I think this is like, yeah, I mean that's the sort of the.
I mean, this is more or less automatic whenever you match the canonical entropy to the microcanonical entropy.
Right. So somehow the black hole information has not
yes,
really gone in.
not really gone in, but you are starting with a TFD state, and the TFD state is dual to this eternal black hole, so you expect it to be S black hole. I mean, it depends on the state.
So somehow that limit is kind of a G neutron going to zero type of.
Yes, yes.
So in that sense, the SPH would be infinite. So it's not so clear that.
Right. I think it will be clear whenever you go to the calculation, because here you are starting with the microcanonical state and finally identifying the microcanonical partition function to the canonical partition function. But anyway, you are starting with the microcanonical state with omega states. So now you get the final result where d lambda is given by minimum of omega and e to the power s. So eventually it picks that e to the power s.
True, but I'm saying that in any of those things, I'm not really seeing the black hole area going. Right? Both of
I see. So you are saying more geometric way of showing itself.
Why is it that this, this particular ensemble that you have chosen is really actually giving you the black hole entropy? Is basically something.
Yeah, this is something I agree. This is in all these calculations actually, also in the PSSY and so on. So they kind of identify this canonical entropy directly as a black hole entropy with area. There is no.
Papers where they put the brains at the black, there may be.
No, but the argument is the same. For example, in the Balasubramanian, the difference is that following. So whenever you have this geometry, right? So what Balasubramanian does, you have these indices here. This indices is my field data, my indices. Balasubramanian et al. Does this different thing. They have the boundary indices the same, but they change the bulk geometry by using different things. Right. So in their case, the bulk geometry changes, but my bulk geometry remains the same as the BTZ black hole.
So, but bulk geometry changing maybe, in my opinion, may be a good thing, right? In the sense that that way you can access, maybe you can connect this canonical / microcanonical entropy to the area entropy of the black hole, maybe using some Gibbons-Hawking type of
you can in principle, but here also, for example, if you think about this, you can think about infinite number of Euclidean black hole spaces. For each of these black holes, you can do the Gibbons-Hawking calculation. The on-shell action calculation, and it will lead to the black hole entropy as area.
Yeah. So I think that see that's I agree. I mean I think that is maybe we can talk about that again.
Yeah. But I'm saying like in this case, just like you have in this case, we do not explicitly do it because since the black hole is already BTZ.
If you did the bulk geometries that are capping off these things,
right,
and choose to interpret it in terms of Gibbons-Hawking type of thing.
Yes, it will be automatically come as area from the on-shell action.
I don't consider the algebraic calculation to be completely the final thing.
No. But I'm saying if you think of, since I'm not changing the bulk geometry, I have only one bulk geometry. So what you can do the Witten-like calculation for the bulk partition function and end up in getting the entropy that is identified with the entropy of the black hole.
In your case, it's a little bit different. I feel because
no, because the boundary conditions do not modify the entropy, right? The boundary conditions, if you have this bulk geometry, this Euclidean black hole, it is insensitive to whatever boundary condition or the field data you put on the boundary, right? So the bulk geometry determines what will be the value of the entropy. So if you compute the on-shell partition function, it will give the entropy from what you should get from the bulk geometry. The reason Balasubramanian had to compute because they added this end of the world brane, and for that they have to take the back reaction of the end of the world brane. So their geometry differs from the BTZ geometry. In our case, we are not tampering the BTZ geometry. We are just putting different boundary conditions. So from the BTZ geometry, we should get the correct area.
So essentially, you are saying that there is a kind of like a tautological translation between the boundary data, this entropy, and the Gibbons-Hawking.
Right, absolutely.
So but I'm not fully happy with it,
but you can Okay, so then it gives you a factorized Hilbert space. As Chetan says, this is the crucial step where you show that if you add non-local corrections, the spectrum becomes discrete, and eventually you end up in getting a factorized Hilbert space. Now I will talk about something Chetan's favorite, my favorite also. So it's just the microstates without horizon, and we'll ask the question, do you have black holes or do you really have blackish holes? So as we said, this is a moving to a complementary picture where we start from a type 1 setup and try to understand whether in any perturbative sense we can mimic a type 3 setup. The type 1 setup we consider is a toy model where the BTZ black hole is put in a semi-infinite box with brick wall near the horizon here. So I think you are already accustomed to this setup from Chetan. So it's the same setup, and you solve for a free scalar field of mass mu in this background satisfying this. Now the setup is exactly the same, but the exercise we will do now is complementary to what Chetan, Arnab and others they have did, and also Chetan later did with his students. So what we do now is to compute the holographic Green's function, assuming the Sonnenstein's prescription work when the brick wall is kept sufficiently close to the event horizon. And this is the picture. You have a Dirichlet wall here, and you have a black hole, and then you put the Dirichlet wall right here and try to compute the Sonnenstein's holographic Green's function. We redefine the radial coordinate as z, so that the horizon at z equal to 0 and boundary at z equal to 1, and you impose a cutoff at z naught, which is greater than 0. The important difference is that with the standard practice is that we compute the retarded Green's function with the Dirichlet boundary condition and not infalling anymore. And once we compute the Green's function, we get a very ugly expression which there is no need to show. But let me discuss the key features of this solution, that the Green's function has discrete poles on the quantized values which correspond to the normal mode frequencies. However, as we move the wall of our box closer and closer to the event horizon, the poles become denser and denser. And the accumulation of the poles occurs both for the m direction and in the n direction. M is the angular momentum direction. However, the accumulation is faster in the m direction compared to the n direction. Good. So now when a low energy observer who sits at infinity stares at the accumulated poles at infinity, it mistakes it for a branch cut. The mathematics of this mistake can be precisely formulated as follows. At fixed z naught, you can compute this, write down this Green's function as a sum over residues. This omega to the power delta is introduced here to ensure that whenever you go to the boundary of this complex plane, you get things goes to 0 consistently. As the poles becomes dense and beyond the resolution of the energy scale of the asymptotic observer, you can change the sum to the integral, and eventually you can show that the Green's function will have a branch cut, and the jump function is given by the imaginary part of the black hole Green's function in that particular limit. So this is the thing that is the important result, that the jump function of the branch cut as the asymptotic observer sees at low energy will be identified with the imaginary part of the Green's function, and this will have a very important consequences. In the limit, yes,
when you put the boundary condition disappears.
That's what is interesting.
yeah, at least in the jump function, I mean, but these are the subleading corrections. This will come in the subleading corrections.
Yeah, so also one thing is to say is that we are taking the limit when z0 is going to 0.
Yeah.
What is somewhat surprising is that the Dirichlet boundary condition when z0 going to 0 seems to give a correlator which has an infall.
Yes.
That is in some sense, surprising.
Exactly. I mean, the reason yeah, exactly. The important part is basically this jump function, because if you compute the retarded propagator, remember another thing is very interesting actually, that came up with my discussion with Shiraz, this NSM. So whenever you are computing this Green's function in, say, the Sonstein's prescription with Dirichlet condition, you are not really computing the retarded propagator, because you have both infalling and outgoing modes for the positive frequency solutions. However, it turns out to be retarded in a particular limit. So whenever you are going very close to the horizon, and that is equivalent of saying what you are saying.
So I think so. I also had a discussion with Shiraz, and I think he asked me a similar question. One of the things I was telling him is that if you take the stretched horizon really close to the horizon, right? So in some sense, the number of wavelengths that the wave has to traverse as it climbs back up becomes infinite.
Yeah, exactly.
So that I think is operationally the reason. Even though physically it is, like Jersey distance is small.
Yes,
the
yes.
wave numbers inside it are infinite.
Yes, exactly.
So
I mean, that's what also I think in the eco paper in Mathur and others, I think they kind of mentioned this. Yes. No, of course, but they have kind of had an extended discussion on this on their paper, that how these wave functions become fast oscillating or something like this. That's correct. So, and technically how it appears, now what happens that whenever in the mentioned limit, as I said, like the effective temperature becomes almost identical to the Hawking temperature of the black hole, and this can be shown by a simple computation of the position space Green's function. If I now go to the position space Green's function, you are doing the integral over this Green's function, and since the residue is proportional to the imaginary part of the Green's function, black hole Green's function, whenever you go to the position space in the leading order, it gives you the position space black hole Green's function. That's what happens. So there is an emergent dissipative behavior as well, that the jump function across the branch cut contains the complex QNM poles of the black hole, and the conclusion is that an asymptotic observer with the energy scale lower than one said by the rate of accumulation of poles, the pure states will look like a black hole. So we can make this construction slightly less toyish by thinking about, it is still toyish but slightly less than before. You can think of a collapsing solution, a spherical shell collapsing into a black hole, a thin shell collapse, what is known in literature. But in that case, what you have to do, instead of the Dirichlet condition, you have to put the matching condition, the Israel-Shane-Langshaw's matching condition, but the result remains very much the same. So the near collapse states becomes indistinguishable from a black hole. And this will also have a very interesting algebraic consequence. We can show explicitly that moving the cutoff near the horizon results in an approximately continuous energy spectrum. And if you use this condition, you will show that the trace functional, as I said, trace functional, the one important ingredient of type 1 algebra is the trace functional you can always define, and type 3 you cannot define the trace functional. Okay, so you can show that you will have a vanishing trace functional in this limit. Okay, you cannot define a tracial state in the limit whenever it moves close to the horizon. This signals a type 3 approximation of a type 1 von Neumann algebra. Note that these vacua are very different. The cutoff geometry is an excitation over the Boulevard vacuum state. I think Chetan had a kind of detailed discussion on this in his paper, one of his papers, I think the last to last, right?
Just to be clear, but it's not quite the Boulevard vacuum because of the stressed horizon.
Excitation over the.
Yeah, it is yeah, I'm saying that the Israel Mokohiyama is basically actually over the Boulevard vacuum.
Yeah.
So it's only heuristic.
Oh, yeah, exactly.
So you definitely need the stressed
Yes,
horizon
yes,
to make
yes.
everything finite.
That's correct. That's correct. What do you mean realistic?
I mean this branch cut, the rate of getting this collision like this goes into the branch cut.
Yes. I mean, you mean, yeah. So this follows from this accumulation of the poles. If the poles accumulate very fast, okay, so you can find the resolution scale of these poles. If you are an asymptotic observer, that is the scale set by this cutoff. Okay, so and you can find how it behaves with the cutoff, and that is basically given by this, like these are kind of these approximate fit functions that you can find, and here this z naught appears as Justin was asking. So it determines how fast it is accumulating, and that from this you can find a energy scale beyond which these poles separations cannot be registered by an asymptotic observer. So it gives you an energy scale for the asymptotic observer beyond which you cannot separate two poles. Okay. So as I said, the vacua are different. However, for a sufficiently low energy asymptotic observer, these two states are indistinguishable. It was an old argument by Israel and Mukawama, and what they were arguing, like if you have a Boulevard vacuum and you kind of augment the Boulevard vacuum with some radiation, then for a low energy observer it will look quite the same as the Hartley-Hawking state. So they will not be seen for, they will not be able to resolve these two apparently different states. And this is also a geometric manifestation of what is known as a factorization map, if you think this way, of Jafferis and Kohlschmer. So what they did, they were asking the question how to compute entanglement entropy in a JT gravity, for example. JT gravity is a trivial example, but still, because you can explicitly compute the wave functional in the JT gravity. What they said, okay, so you have a black hole spacetime, so now JT gravity spacetime, and then you kind of chop it off with a brick wall, but you put a defect CFT operator on the brick wall, okay, and now they compare this wave functional of this defect operator and compare with the Hartley-Hawking wave functional, and by that they read off what kind of defect operator they have to put, and they call this map a factorization map. This is essentially the same told in a different way.
So that is also that's the Jafferis-Kohlschmer.
Yes, exactly.
And that is in JT gravity.
That was in JT gravity. But I think this is what we are doing is actually the same as the factorization map. You can, if you connect it to this story, so you have a type 1 algebra which approximate, or if you proceed in the other way around, you say, okay, so I have a type 3 algebra, I approximate with a situation up to energy scale we cannot distinguish, and for this case I can compute the entanglement entropy. I can put any cutoff anywhere and I can compute the entanglement entropy. So now you can put a cutoff. I mean, that's also an interesting question. Now suppose I put a cutoff such that I want to reproduce the black hole entropy. Yeah. Is this possible? That's a...
Yeah, so that I think is what all these things do.
Yes.
So,
yeah.
But I somehow the way you're presenting it, seems to me, I mean, I'm going to be more biased than you are. So you're starting from type 3 and going to type 1, and the other way is going from type 1 to going to type 3.
Yeah.
I would say that the second approach is more legit, in the sense that, because we know that if you have a single CFT, the algebra is type 1.
Yes.
Right?
Yes.
We know that type 1 is the real deal.
Yeah.
So, I'm not,
No, I completely understand. Only thing is that I have worked with, so I'm biased about both. But the point is that I should also mention the loophole about this compared to that. The reason that thing is in some sense better, the first thing, is that you know what are exactly these non-local corrections. In this case, what you are doing, you are these non-local corrections or the UV completions, you are hiding inside this cutoff.
No, but I would say the other way. I would say that it is the fact that you have a two-sided black hole is the reason why your system is originally two-sided.
Yes.
Sorry, non-local. Because you have the freedom to do this alpha shift.
Yeah.
Or alpha or any other shift. But the point is, by incorporating the non-local corrections, you are compensating for the non-local things that are inherent in there.
Yes,
so
indeed.
Finally, at the end, you're again trying to get to type 1, right?
Yes.
So I mean,
That's
that is
right.
the sense in which I would say that, like, so you're doing that.
Yeah, exploiting this non-local feature of gravity to say that, okay, I distinguish what are the real non-local nature, I put it in my computation, I get rid of this non-locality and get a local theory. That's all.
Yeah,
that's all we do.
That's what I would say that, yeah. So.
But these are the two interests, because I'm saying even there I start with type 3 and then add this non-local corrections, or like compensate the non-local corrections, whatever you say. And in the other case, you start with a type 1. I know that I'm starting with a type 1 theory.
But the fact that so you did not present in terms of the hard locking correlator, but if the emergence of causality,
yes.
you can formulate it in terms of.
But that is already in the, for example, the same calculation is the Green's functions. If you compute the Green's function.
I'm saying that if you do that, then I mean there is no. We know that that's an emergence of type 3.
Yes, indeed.
So all of that is kind of goes through.
Exactly, but there is no way to decide, of course, whether there is a complementary. The point is that I think I would say, like, the first approach supports complementarity and the second approach supports fuzzball. So now.
But I would say that see that one of them is type 1.
Yes.
And we know that a single safety is type 1.
Yeah. Okay.
So that I think is a very important distinction. So type 3 is so when you get a type 3 out of a type 1. That is, you can say that it is an approximation.
That's correct.
Yeah,
but
purely from a CFT point of view, we know that it is type 1.
I completely agree. But only thing is that here, I would not say loophole, but you can also think about this loophole as a beauty, is that, okay, so whenever you have this cutoff, this cutoff you are putting as a bench marker of your ignorance.
Correct.
Of the UV completion.
I agree. It's definitively a finite ingredient in the bulk that we are putting in.
Yes.
But with that one parameter, you can get complementarity in the end-going infinity.
Yes.
So I think complementarity. I don't think it is fair to say that you don't get complementarity, because the moment you get a hard locking correlator, all the thermophile double stuff you will get.
Yeah.
So in that sense, I don't think it is
well, yes, okay. No, but another thing, I think I was just thinking that this is.
Hard locking correlator together with factorization. If you get it, then I think you're.
Yeah, I agree. I like both. I mean.
No, I'm not pushing you to get it.
No, it's fine, but I think I like both, and this is also this beauty, as I said, like you have hiding all the non-triviality of the UV into the cutoff, and that is also another interesting distinction between the previous construction and this construction. Okay, let me put it this way. As you said, like it is type 1. The reason is that this object, the solution that you are writing, is not a solution of a semi-classical theory of gravity.
So yeah, if you think of quantum equivalent curve space in any sense, that would be the case.
Exactly.
So here is what I would say. So I think I would claim that your happiness with the two-sided thing is sort of fictitious, because it hides the inference in ignorance about the UV complete description.
Right.
The UV complete one-sided description in the bulk you do not know.
Right.
And so this lets you kind of forget about it. Start with the two-sided semi-classical thing. Do this, non-perturbative one-over-n corrections. Let's say that it's all, fine and everything, and get this. So in that sense, it is not that it's only by not addressing the question or asking the question that you're avoiding, this thing, and not like it's not a legitimate way of.
I see your point, but okay, but I will say I would say this is a complementary approach, because in the second case, I would say, like, it's more interesting because you are claiming that I am not starting from any semi-classical solution, because the solution, I mean, that's the difference between the Balasubramanian et al. Construction. If you look at the Balasubramanian et al., they are putting an end of the world brain behind the horizon and solving it. You are computing the back reaction of this brain in the whole Einstein theory of gravity and computing it semi-classically. The important point about this geometry that we are working together is that in this geometry, it's not a solution of any semi-classical gravity, simply because if you put something outside the horizon, you cannot get a solution to semi-classical gravity.
I have some comments about that actually, but that part I agree with. But I think the thing that I would say is that it's any time you do quantum filter in curved space.
Yeah, the point is that I am starting with a semi-classical gravity. You are starting with a full quantum gravity, or you are not. We are starting from full quantum gravity.
Yeah, I don't. It's a
regulated full quantum gravity. But whenever I say it's type 1, you are starting with the full quantum gravity, not the semi-classical limit of it. I think now we both agree. Oh, okay. So conclusion is that we think about two classes of microstates. Okay. I'm biased about both. And the microstates with horizon, we have phase shifted TFD states, non-locality quantified in terms of phases, gives rise to state average replica wormholes in the Euclidean path integral, and these replica wormholes make the dimension of the Hilbert space finite and make this more thing isometric. And without the horizon, we have figured out the limit of cutoff geometry or faithful microstates, and this could be viewed as a manifestation of the factorization map. What I'm trying to understand precisely what are the connection between these two pictures, whether we can counting the microstate can be redone in the second class of microstates. For example, I have in mind, if I think about getting this cutoff very near the horizon and think about microstates for different values of R0, say I take from R0 to R0 plus delta R0, and whether I can somehow locate this non-locality in terms of this cutoff, of course. Okay, so other things that I've been trying to understand is the connection between the non-isometric map and state dependence in the context of phase shifted TFD states, and that is also because we are talking about these TFD states at late time. So as we were discussing the other day, like the state dependent construction of Subrat and Kyriakos is not clear how it will work at the late time. Yes, after page time and so on. After page time and so on. But there was a recent paper by Balasubramaniam et al. Who kind of postulates like this non-isometric map, the non-isometric nature of this map is related to state dependence for a generic setting, and this alpha dependence of the TFD alphas are actually a state dependence in the, for example, as I was mentioning, you have these GNS Hilbert spaces with a particular index alpha. So these are kind of the manifestations of state dependence. So I'm trying to understand this, and thank you very much for your patience. Sure.
I think we are assuming continuum density. I mean, like we're assuming lambda is infinite. I mean, the number.
Usually that's the setting in which it is done.
Yeah.
It's some approximation is being used. I mean, because it is finite. Like suppose G squared is.
No, I think I take back my word. I think this is infinite. Yeah. I think I'm taking lambda to be running up to infinity really. Because otherwise.
The question is, how does the dimensionality come in? Yeah. So actually.
So.
But I've seen Balasubramaniam et al. Also maybe like
some way of thinking about it.
Yeah.
So only thing I know, like they are writing this down for like the to infinity, and all they are counting since they are counting the rank, they are only interested in the eigenvalue density of this lambda.
I think some sort of density idea comes in, and then it's
because you can see finally you are integrating this eigenvalue density with this d lambda from 0 to lambda, 0 to infinity or epsilon to infinity as for the cutoff.
I think what is happening is that you're taking n going to infinity, but there is a density. There is some
density of eigenvalues which are finite. Yeah.
So that's what you look for.
Yes, exactly. That is what gives you the rank by integrating the density of eigenvalues. And I think I have also some result for the density of eigenvalues. It is given by a simple polynomial.
Integer, right?
No.
You make a quantity.
No.
Because it is really something.
So that's what it is written as this as a minimum of these two things.
But I think it is actually part of the standard Phoenix model. I think you just have to look at precisely how it is written.
Yeah, I have also these calculations. I mean, yeah.
Okay.
Yeah.
Questions? Let's thank Shalvi for a thought-provoking talk.
Can I ask another question?
Yes, of course.
Why do you say that quantum gravity was type 1?
Who says? Chetan said.
Your the slide was there.
I was telling? I thought Chetan was telling.
But I say,
Yeah, but it's fine. But depends on what do you mean by quantum gravity. So if I think about semi-classical gravity as a solution of Einstein's equation, then it is type 3. By full gravity, you mean like the gravity plus all sorts of perturbative and UV completion and perturbative, non-perturbative corrections taken into account. Then there is no reason to expect that it will be something different from quantum
I
mechanics.
think the basic one way is an ADS CFT. We know that the CFT is always type 1. The full Hilbert space of any theory is always type 1. So, and we know that quantum gravity in ADS is given to this, then it cannot be type 1. That's one, So that's why in his computation he needs 2 copies of that. So, it's already, you know,